Okay, so the last speaker for this session and also I think for the day is Amanda Zhu from University of Wisconsin-Madison, and they're going to talk about synthesizing quantum circuit optimizers. So go ahead.
Thanks for the introduction. Hi everyone, I'm Amanda, and today I'll tell you a little bit about what a quantum circuit optimizer is and how you can synthesize it. For a while now, we all had this dream of quantum computing, and it's that one day that we'll have these machines that may be able to perform some types of computation beyond what we've been able to achieve classically. And if this dream is realized, then we'll be able to have a domain-specific accelerator for types of computations such as drug discovery, simulating quantum mechanics, or machine learning. However, as just an example, this is Google's roadmap for development. And as you can see, the arrow indicating where we currently are is very far to the left. And we simply don't have the machines today capable of performing the types of computations I just mentioned. And it'll be another 5 or 10 years, and that's so distant that the meantime has been given a name. It's called the NISQ era. And NISQ stands for Noisy Intermediate Scale Quantum Computing. And the key word here really is noisy, because every quantum operation will introduce some probability of failure to your computation. And to get into how these errors affect your computation, let's look at what a quantum program looks like. So this is a program, or otherwise known as a circuit, and it's very simple. It's just a sequence of gates applied to quantum bits, or otherwise known as qubits. And the problem is that each of these gates here introduce some noise to your circuit, and if your circuit is big enough and you have enough gates, then these errors will accumulate to the point where your computation will be completely lost and indistinguishable from random noise. And so an objective for a compiler might be to minimize the gate count to maximize the success probability. And so far, compilers use manually derived optimizations to accomplish this. And that may seem fine, but the current state of affairs is that we have all these different types of hardwares being developed. For example, we have superconducting computers, ones that trap ions for their qubits, or others that use neutral atoms, and even ones that use photons. And each of these hardwares have their own gate set, or you can think of it as an ISA in the classical setting. And because the physicists are constantly experimenting and trying to modify these hardwares and improve them, these gate sets are in flux. And so even though, even for the same hardware, the gate set may change, like it did in IBM's case. So ideally, we don't want to rewrite our compiler every time something changes, and we don't want to only rely on manual optimizations. So this is where the synthesis problem comes in. And that brings me to our tool, which is called QUESO, and it stands for Quantum Equivalence Synthesizer for Optimizing. And the input here is a gate set specification, and then QUESO will synthesize an optimizer for that gate set. For example, if we're given the IBM gate set, then QUESO can synthesize an optimizer in 1.2 minutes. And when we compare against state-of-the-art optimizers using manually derived optimizations, we can vastly outperform them. And notably, here, Qiskit is IBM's own compiler, and it's one of the most popular ones used in the community today. TKET is another industrial compiler developed by Quantinuum, and Vox is a verified compiler in Coq that was presented at POPL 21. And before I get into the details of what a quantum optimizer is, let's just have a quick refresher on what this means in the classical setting. you may recall from your undergraduate compilers class that an optimizer can just apply what's called rewrite rules to optimize a program and rewrite a program into another one that is better by some cost metric, hopefully, and also preserve the semantics of the original program. And now to talk about what quantum optimizations look like, we'll have to cover some quantum computing fundamentals. So in the classical setting, we all know what a bit is, and it can be either 0 or 1. And if I'm in the 0 state, I can negate it, and I'll get to 1. And in the quantum setting, our state is just now a vector, and we also have something analogous to the 0 and 1. These are basis states called QUET0 and QUET1. And if we negate the QUET0 state, we'll end up in QUET1. But we can also apply other operations, and the state can be in a superposition between these two basis states, or really the vector can be anywhere on this sphere, and operations can rotate it and move it around. So for example, one operation is called the RZ gate, and from the name you might think that it rotates around the z-axis. So a very simple rewrite rule that involves this RZ gate is just two adjacent RZ gates on the same qubit. If I apply the first gate, then it'll rotate it by pi. And then if I rotate by pi again, it brings me back to the same place I started, so we can cancel these gates out. And then another example of a simple rewrite rule, but with some multi-qubit gates here, is that two adjacent CNOTs operating on the same qubits also cancel. And just an example is that here it's like it flips it, and then if I apply the next CNOT, it flips it back to where we started. Now I'll talk about a more complex optimization. Here we see that we have these RZ rotations by pi, just like before, except with some small differences. Here they're no longer on the same qubit, and they're not adjacent. There's this subcircuit separating them. So now it looks confusing. But it turns out that if this subcircuit, highlighted in yellow, satisfies some constraint, then we can indeed rewrite this, and we can merge these two rotations onto the same qubit. And the rewrite rule that allows us to do this looks something like this, where we have a RZ rotation by some arbitrary angle theta, and then we have a symbolic circuit that satisfies some constraint, and then we have the other RZ rotation by another angle. And this can be rewritten into the same symbolic circuit followed by the two rotations merged. And now that we have a taste for what these optimizations look like, a very simple algorithm to synthesize it would be to start out with no rules and then enumerate all the possible circuits up to some bounds. And then now I want pairs of these for rewrite rules, so I'll iterate through that. And then check each pair, and I'll add it to my rule set if they're equivalent. But there are some problems here. First of all, the set of circuits is going to be big, even for some relatively small bounds. And now I have this quadratic explosion over this set of big circuits. And then finally, we need to verify, and it's unclear what this really even means for symbolic circuits because we haven't given a notion of what their semantics look like. So as an overview of our approach, we take in potentially a symbolic circuit, and then we convert it into a polynomial. And then we invented this data structure called the polynomial identity filter, from which we can get circuit equivalence classes, and then it's very easy to extract rewrite rules from those. And we put the polynomial through the filter, and it will put it into the equivalence class. And there are two key underlying ideas here powering this pipeline. The first being Feynman's path integral formulation for quantum mechanics. And then the second is the short-stipple lemma for polynomial identity testing, which is just a procedure for checking the equivalence of polynomials. So first, I'll dive into Feynman's path integrals. Using the path integrals, we can define what's called the path sum semantics for quantum operations. And this is a more compact and algebraic representation for semantics of gates. And it looks like, you can think of it as like a transition relation between states for operational semantics. And we have the RZ gate here from before. And what it does is it takes in the state and then applies this amplitude factor here, but it leaves the state otherwise unchanged. And then the other gate that we saw before was the C0 gate that operates on 2 qubits. And there's no amplitude factor added here, but the state is modified, and we put the XOR of the 2 inputs into the second qubit. And more generally, for gates like these that don't put the state into superposition, we can represent their semantics like this, and we have this phi function for the amplitude, and then the f for state, and these are just transformers for those. Now that we have these semantics, we can define what the semantics look like for a symbolic circuit simply, and it looks like just what I had in the last slide, except now the amplitude and state transformers are symbolic uninterpreted functions. And now to give a rough example of how you might use these semantics to transform a circuit into a polynomial, I'll walk through this circuit, but if you want to know all the details of this transformation, you can look in the paper. So to start off, we have this RZ gate on Q1, and we want to iterate through the input basis states to get a sum to be the polynomial. And so we can, if we have ket 0, then this is the term that we get. And if we simplify it, it turns into this. And then we can add on what this circuit would look like on ket 1. And then if we have a symbolic component of this circuit, all we need to do is constrain the state transformer. And here, to keep things simple, it's just the identity. And then the polynomial looks like this, where we just have these extra phi terms representing what the output of the amplitude transformer would be on these input basis states. And now we have something that looks a lot more like a polynomial, although there are some details missing. And there are some, you can see that there are some special variables here that will need to be constrained because these are complex numbers on the unit circle. And now we have a way of turning all the circuits that we had from before to a lot of polynomials, but we still have the problem of this quadratic explosion from before, and that's where polynomial identity testing will come in. So polynomial identity testing is just the problem of if I have this polynomial P1 and I have another one P2, and I want to check if these are equivalent, and hopefully the check that I use will tell me that they're not. And the simplest thing that you might think to do is take a finite subset of the complex numbers and sample some values uniformly and independently, and then plug them into the polynomial and evaluate, and then check that they evaluate to the same value. And for such a simple algorithm, you might be wondering what the correctness guarantees are, and that's what the short-stipple lemma gives us. It says if these two polynomials are not equal, then the probability that they evaluate to the same value is very small, and it's at most the maximum total degree over the size of the domain that you sample from, which you can make arbitrarily large. And also, intuitively, this is the probability that you unluckily sampled a root. To see how this helps us in the polynomial identity filter, we want to have a data structure where we just insert a polynomial and it puts it into the correct equivalence class. But it's kind of unclear how we'll do that. Luckily, we can have a fixed random sample, and then we can evaluate this polynomial, and then insert it simply based on the value that we get. And here, we put P3 into the same equivalence class as P1, and that means that they should have evaluated to the same value using alpha. So now, to put this all together, our polynomial identity filter from before looks more like this. And instead of circuit equivalence classes, because we're extracting rewrite rules, and then these are all the circuits that we've enumerated. And if we pick one, we'll turn it into a polynomial, and then we'll insert it like I described in the previous slide. And then the failure probability is bounded by the union bound. And if you recall from before, the polynomial identity test has a failure probability of d over the size of r for each test that you do. And in this case, we're implicitly doing k-squared of those because that's how many pairs we have. So our failure probability is k-squared d over the size of r. And as a quick example, if we insert 1,000,000 mutually inequivalent polynomials of degree 10, and we sample using the 64-bit integers, then we get something like 10 to the negative 7, which is quite small. And these are the same results that I showed from before, but just in a little more detail. So for the IBM gate set, we synthesized 701 rules in 1.2 minutes, and the failure probability is around 10 to the negative 17. And to read these graphs, each point is a benchmark, and if it's above the dashed line, then we outperform. On the dashed line, we match, and below, we underperform. And the y-axis is 2-qubit gate reduction because it's critical to reduce 2-qubit gates since they have at least an order of magnitude higher error rate than single-qubit gates. And as you can see, we're doing quite well here. And if you're familiar with this line of work, you might be wondering how we compare against Quartz, which is a super optimizer for quantum circuits that has some similar ideas because they want to synthesize these rewrite rules to super optimize. But some key differences is that we have this notion of symbolic rewrite rules, and Quartz is applying a preprocessing phase with some domain-specific optimizations that we're not doing. So to compare just the synthesized rules head-to-head, we have the graph on the left here where we take away preprocessing from Quartz, and then the graph on the very right where we add preprocessing to QUESO, and we can see that we do very well. And then when we have both tools unmodified, we still outperform or match on the majority of the benchmarks. And of course, there are more results in the paper on other gate sets and some other experiments that we ran. And to wrap this up, I'll briefly talk about future work. Something that is missing from this talk is how we applied these rules, and that's because it's a very simple algorithm at the moment. And it would be interesting to see if we could use the new version of EGG to use equality saturation to speed this up. And when we were developing this, it wasn't mature enough for us to use. And alternatively, we might look into reinforcement learning for scheduling these rules. And then another avenue would just be to look if we can have more enhanced rules and capture some optimizations that circuit resynthesis can get, or we can explore approximate rewrite rules. And with that, thanks, and I'm happy to take any questions.
Thank you, very nice talk. I had a question about the evaluation. If I remember correctly from the paper, you essentially compare quantitative measures on the resulting circuits, right? Number of number of quantum gates, number of qubits, stuff like this.
So if I understand the question correctly, you're asking about the metric that we're showing here?
Yes.
Right, yeah, so we're mainly looking at 2-qubit gate reduction, and and we also have some results in the paper on circuit fidelity, which is the success probability of your circuit. Basically, these two line up very closely because the dominant error is from the 2-qubit gates.
Have you by any chance found use cases or applications of this work where we actually looked at concrete algorithms and did you synthesize, you optimized optimization on these concrete algorithms and saw then improvements in validity or fidelity or any kind of measures for this specific use case?
If I I'm not sure if I understand.
Okay, so you kind of compare these circuits in the wild, and they are and your results are astonishing. But have you done, for example, a quantum Fourier transformation and did then the optimization with various forms and come up with better runtimes on the hardware or the better simulation times or other features which were interesting?
I'm still not sure if I understood.
Okay, maybe
but,
you can take it off then. Thank
yeah,
you.
I can take it off.
Hi, very cool work, thank you. So one class of relevant optimizations that people use in practice is to actually trade off the number of qubits with the number of gates, right? So for example, adding extra temporary qubits in order to decrease gate count. This has the side effect of actually changing the size of the state space, right? I was wondering if you had considered these optimizations or if you foresee any difficulty using a similar approach for them.
Yeah, that's a good idea. I think that's something that we could explore, and I think you could increase. Maybe you could have rules that have more qubits and smaller, and see if that enables any additional optimizations. The only problem I can think of is that as you increase the number of qubits, of course, this process will grow.
Would the polynomial identity testing technique still work if your polynomials are going to be over varying sizes of circuits on the left and right side?
So if I understand correctly, you mean if they have different numbers of qubits?
That's right.
Yeah, you can always extend, we actually talked about this in the paper, you can always extend a circuit to include more qubits that are just not used, and it will still work.
Yeah, I guess that would work. Thank you.
Hi. Yeah, this is a great talk. Thanks. So in terms of the scalability of that first arrow there, where you're going from the circuit to the polynomial, I'm really curious like what that is and the limitations of that, because that seems critical. And it's also really, I think it's a great idea to like use that once you have that to like fully characterize the circuit and then test for equivalence. So like it hinges on that first step. So I'm curious kind of how far you pushed it, you know, like how far were you able to go there?
Right. So you're asking how, I guess, how big of a circuit can we convert to a polynomial? Right.
Yes.
So I believe the biggest circuit, all these rules used in our evaluation have 3 qubits, up to 3 qubits, and the largest size has 6 gates in for one of the gate sets. So yeah, you're right though that there are some limitations here if you want to go bigger, because we are enumerating all these basis states. But the idea is that for rewrite rules, like typically you don't need to get very big in order to have something useful. So
Sure, makes sense. Yeah, thank you.
Okay, let's thank the speaker again. And with that, we conclude the session.